So now we're going to look at applying the second derivative test to some problems. So on page 216 of your book, where you will have some homework, we see use the second derivative test to find the local extrema for the function. So some things coded in this question. It says find the local extrema, all right? Global extrema are also local. So when they say find the local extrema, we're really just finding all of the extrema and not bothering to say whether they are local or absolute. So we don't have to, all right? Next thing, it says find the local extrema. It doesn't say find the value of the function. It doesn't say find where the value occurs. It just says find the extrema. That means it wants both the x and y coordinates. So we want to find a point that is an x and a y coordinate. All right. Now, you have really two derivative tests to identify maxima and minima. Second derivative test, first derivative test. Polynomials are where the second derivative test shines the brightest. Because the second derivative is easy to get, polynomials are differentiable for all real numbers, so you can always find that second derivative. So second derivative test is usually your first go-to on a polynomial. On something else, you might use something different. You might use the first derivative test. Remembering that the second derivative test is easier but does not always work. The first derivative test is usually harder and always works. But polynomials lend themselves to second derivative tests. All right, no matter which test you're using, you have to start by finding the critical points. That's a given. Anytime you are finding the extreme values of functions, you must start by finding the critical points. You find the critical points by setting the derivative equal to 0. So we're going to say y prime equals 5x fourth minus 80 equals 0. Sometimes I say for calculus, if you're not sure what to do, just find the derivative and set it equal to 0, because that's how you solve most things in calculus. So we're finding maximum values of functions. All right, so solve this equation. It's pretty easy to get from here to x fourth equals 16. Remember, if you have x fourth equals 16, the x equals plus or minus 2, because you're taking an even root. If this was an odd power, I would just have the positive value, or negative, or it would keep the sign of whatever it is, right? So an odd power is just going to keep whatever sign it has. An even power is always going to pick up plus or minus, and even power has to be equal to a positive number, or there's no solution, no real solution anyway. And here in calculus, we don't yet mix complex numbers in. You don't mix that in until after you finish all your calculus, and then you do something called complex variables. All right, so here's our two solutions. We want to use the second derivative test, so we can just say SDT. We'll start on x equals 2, and we'll observe that our second derivative test, our second derivative is y double prime equals 20x cubed. All right, that's our second derivative. We're going to use it on x equals 2. So to use it on x equals 2, we're just going to say, what is y double prime of 2? Well, it's 20 times 2 cubed. And I can sit here and work out what that is. It's not too hard. It's 8 times 20 is 160, okay? But you do not need to. Test-taking strategy, you do not need to know what this number is. You need to know whether this number is positive or negative. As soon as you have y double prime of 2 as positive, we already know that the function has a max there, so we can already state our conclusion from the second derivative test, which is that y has a min, because y double prime greater than 0 is a min, at 2. Now I said we wanted both the x and y coordinates, so we're going to take this 2 and plug it back up into our y. So I'm going to have 32 minus 160 plus 100. So that's the same as 32 minus 60, which is a negative 28. So negative 28. Now your justification on this, as long as you have said y double prime of that value is greater than 0, then you justify this by saying by second derivative test. And you can write that as free response on your AP exam, and they will know what SDT means. And you'll be using this so much you'll remember it. So you can use that abbreviation SDT. But if you're a person who likes to write everything out and be super explicit, you can say by second derivative test. All right, now we're going to use that SDT, that second derivative test, on x equals negative 2. Negative 2. So then we're going to say what y double prime of negative 2 is. Well, that's equal to 20 times negative 2 cubed. I don't have to figure out that that equals negative 160. All I have to do is say it's clearly a negative number, because I cube a negative, it's negative. I multiply times positive, it's negative. All right, so you don't have to work that out. So I can state my conclusion here that y has a, because y double prime is less than 0, has a max at 2 comma, let's see if this is negative 2. plug -2 in up here. I have -32 plus 160 plus 100. So 260 minus 32 is 228. All right, you don't need a calculator for that, but you can. By second derivative test. This could be a calculator inactive question. No reason, but you would need a calculator for this. Okay, and that concludes this question. All right, you're done. You have found all of the extreme values. The extreme values can only occur at critical points because there is no interval, so we don't need to check the endpoints. If there was an interval, we would check the endpoints. This has no interval. We're just going to look at the critical points. We use second derivative test to determine that this point is a min, this point is a max. Justification in both cases, second derivative test. We find it by taking that critical point and plugging it in to the second derivative and evaluating that and see if I get a positive or a negative. All right, so that's done. I do want to make some additional comments about it now, about sort of the value and power of this. So here's a quintic polynomial, right? And all right, I could graph this on the graphing calculator, but I might have question as to what I see. If what I see in the window, everything that the function does, I might not know that. So and you could expand the window, which maybe something's happening right outside the window. I don't know. When you graph this, here's what we know everything about this function. Also, by the way, in terms of setting the window, we could set the window ahead of time. You wouldn't know that this function goes up to 230 already at -2. All right, so we can make a sketch of this very quickly. Here's 2. We'll just scale our axes to be whatever we want. So here's 2, -28. Here's -2, 228. I'll just say it's right there, 228. So that's that point. All right. I can do some extra stuff that's very easy. Like I can see that the y-intercept is 100. Put zeros for the x's, I get 100. So the y-intercept is 100 right there. Now, I know everything that this graph does. There's a max here, a min here. There are no other critical points. Therefore, this graph cannot do anything other than go up forever and go down forever. All right. Now look, this being a quintic graph, we know that for a quintic graph could have up to 4 turning points. All right. So just from what you know from Algebra 2, this graph, for all we know, could go like this, right? And this graph could have up to 4 solutions. If I set it equal to 0, this graph could have up to 4 solutions. But I know that for this graph, I now know that that's not the case. This graph has 3 solutions if I set the original function equal to 0, and it only has 2 turning points. Cannot do anything else outside of what we see here. So if I see a graph and I see these 2 turning points, if all I knew was Algebra 2 and I had quintic, I think, well, all right, I see 2 turning points, but there could be 2 more somewhere that I'm not seeing. All right, but with calculus, we know there's only 2 critical points. There can only be 2 turning points. And I know that this one's a max and this one's a min, and I know their values. All right, so we'll look at some more examples next.